Hello, and thank you for joining us for today's webinar, Smart Parts, Additive Manufacturing for Integrated Electromechanical Devices. My name is Kim Kaloran, and I will be your host for today's event. Before we get into today's topic, I wanted to give you a little overview of who Stratasys is. For those of you who aren't familiar with our company, Stratasys makes 3D printers and production systems based on patented fused deposition modeling, or FDM, technology that can produce prototypes and production parts directly from 3D CAD data using engineering-grade thermoplastics. We also operate Red Eye On Demand, which is an online rapid prototyping and digital manufacturing service. And as you may have recently heard, Stratasys has merged with Objet, which is an Israeli-based manufacturer of 3D printers that use inkjet-based polyjet processes to create a 3D model. So let's get into what we're talking about today. I'd like to welcome our two speakers, Mr. Jeff DeGrange and Mr. Bill Macy. Bill is the Application Development Lead for the Stratasys Direct Digital Manufacturing Group, which is a team of experienced manufacturing technology professionals who act as a resource for manufacturers in high-requirement, high-certification industries like aerospace and defense. Bill's background includes 20 years of aerospace design and manufacturing experience, including mechanical engineering at Boeing and McDonnell Douglas. And Mr. Jeff DeGrange is the Vice President of New Business Development and Direct Digital Manufacturing at Stratasys. Jeff has more than 20 years' experience in manufacturing technology, including leading an advanced manufacturing research and development program at the Boeing Company as the Senior Technology Manager. Prior to Boeing, Jeff held positions at McDonnell Douglas Aircraft and Raytheon. So now, without further ado, Jeff, I'm going to let you kick this off.
Well, thank you, Kim. I'm delighted to talk about the smart tools and smart parts technology and how it's really leveraging the additive manufacturing technologies, not only the technologies offered by Stratasys, but also the technologies offered by Optomec. And what we're going to cover in this presentation is basically how these processes work individually, how they then work in a combined process, what's really the output they deliver as far as applications. And then people will say, well, what's the advantages of marrying these technologies together per se? The advantages, and then what you have to think about when you actually do this marriage of additive manufacturing technologies and what the future state might look like. So when I start talking about marrying two additive manufacturing technologies together, in particular I'm talking about the fused deposition modeling, the FDM technology from Stratasys, which basically uses a series, there's a number of different types of engineering thermoplastics that we can extrude with the FDM process. The Optomec aerosol jet, AJ for short, is a way that they actually print circuits onto non-planar surfaces, and is typically a nanoparticle silver conductive material that gets printed onto a surface. So why do we do this? You know, we talked about fully printed hybrid structures. So for people out there, they want to know what a hybrid structure is. Well, what is a hybrid structure? Well, from our opinion, a hybrid structure is, if you ever think about if you ever taken a radio apart or any type of device apart, electronic device apart at home, and you look inside it, you got wires, you got circuit cards, and so that's basically hybrid. You got printed circuit boards, you got wires that attach different power sources, and how do you actually minimize the amount of components that go into that? And the number of wires, the number of connectors, the number of clips and brackets to hold down the different wires? How can we actually use the power of additive manufacturing to actually eliminate the number of components, the connection points, and combine that together? And that's what we're considering to be hybrid, is to be able to integrate a 10-piece assembly into maybe a 1 or 2-piece assembly by using the power of additive manufacturing in this particular case. And where this really has kind of come to life is some of the bringing it into the real world now and relating it to areas that we can kind of visualize and see that the value of doing this integration of technology is with an unmanned air vehicle wing. the audience may or may not be aware of that there's a big emergence on multiple fronts as far as what we call unmanned air vehicles, or commonly known as drones. Lots of drones that fly. There's lots of drones that are on the ground. I certainly hope maybe one day in the future I can have a drone to wash dishes at my house and vacuum the carpets. But you know, and you start thinking about these drones. It's electromechanical, and there's electronics into them. There's plastic structure into them, et cetera. And how can we apply these technologies to actually make more efficient design drones and improve their performance? And that's what led us into a research and feasibility, proof of concept feasibility study with the Optimec team. We're both conveniently located in the Twin Cities. We're in the additive manufacturing industry. Both companies have been in the additive manufacturing industry for decades, since they're so close in town. And we really don't compete. They're really complementary technologies. When you sit back and you look at them, even though we're in additive manufacturing, we're very different technologies. And so we just said, hey, let's try to marry these technologies together just on our own, and did some sample parts and said, hey, this stuff works. And then you're going to hear about a project here from Bill Macy shortly that gives you a little more details behind that. But that's kind of how we got started with a joint project, is saying that there is a need out there. How do we take additive makes complex structures very easily from the CAD designs? How do we take it a step further? How do you make something that's just a plastic part or a plastic tool and give it intelligence with ease? And so that's what's striving and thinking here, is how do we actually give it that intelligence? So now I'm going to move into talking about, industries and applications. And this is just a short list of some of the industries. Obviously the aerospace industry. And when you start looking at hybrid structures, the integration with airplanes, both for commercial and military applications, getting lightweight structures reduces fuel consumption. And that's a very positive thing. So if you can find ways to continue to remove weight from airplanes and improve fuel efficiency, the airlines will give you a big hug. And so that's a key area. And then we move on to automotive. We all pretty much own cars and drive and depend on our cars on a daily basis. Is automotive. Now, where could this go in automotive? For those of us who might be engineers or just kind of have the knack of kind of taking things apart to see how things work. You ever taken a dashboard out of a car and see all the wires and connection points behind a dashboard? Or you ever put a radio in your own car and see all the wires and connection points that's behind your dash or console of a car or truck? Just think if we could actually reduce a lot of those wires, a lot of those connection points with having an integrated piece of structure. Weight reduction, faster performance of electronic signals and connection points. So consumer electronics, many different fronts on that front of what we could do, anything from some of the 3D interconnects for stacked dies and complex packaging applications, which is a very interesting one for consumer electronics. And then lastly, the medical industry. When you start looking at various types of prosthetic devices and other types of medical devices that you can now actually sense temperature, sense pressure, sense into very complex tools or devices that would be used in a medical application. So there's a very vast application space and touches many different industries. And that's what's so exciting about this endeavor. So the advantages of the technologies. So if you're staying back and saying, hey, Jeff DeGrange just sounds really great, but, really what are the advantages here? I did talk about, reducing weight. That's very real. Having energy-efficient structures, reduced part count, are very critical in many different industries. When you reduce the part count, you reduce the amount of time it takes to assemble things, to check things. So that comes with real cost savings and real cycle time savings. And when you say, when I talk about connection points, there's fewer failure modes at connection points. Can you imagine taking wires, and at the end of wires you take your red wire and then you screw it to another red wire, and then you put an electrical cap on it, and then you do that, continue on down the line on that? If you can eliminate all those connection points, and then the little clips and brackets that have to hold the wires down, and how well did you tighten some of the wires? You know, that's what we talk about failure modes. So typically in an electrical system, that's a wired electrical system. It's those connection points when the cars vibrate or vehicles vibrate, often will break apart and you'll lose a connection, and then something doesn't operate properly. So what are the benefits of this? You know, the more complex the geometry, we're not talking 2D planar geometries like you would have with a integrated circuit card that you'd see in your computer at home. We're talking very complex shaped geometries that now you can print electronics onto those surfaces. You can do that with less waste, fewer steps, as I mentioned, be able to go use your CAD files and your upstream engineering definitions and data to build exactly what you want, not only from a structure perspective, but then from an electronics perspective. You can integrate that all into a nice package. And so that gives you tremendous flexibility. And from all of that, too, because now you actually can tie everything and have the digital thread from computer file to final part, the cost reduction and the schedule reduction can be very easily recognized for a number of different industries, businesses as we go forward. Now we're going to go into a deeper detail here, and Bill Macy from Stratasys is going to pick it up and step you through the process of FDM and Optimec and hybrid structure.
Hey, thanks, Jeff. I appreciate great lead in there. Today what I'm going to give the audience is an idea of a detailed project in which we were able to integrate the electromechanical design at the digital level. We're really excited about how these two technologies come together to enable us to do new and different things that we could not do in the past. So as Jeff talked, we're working on two processes in series where fused deposition modeling, or FDM, is the first process which was used to build a wing structure. FDM is the process that is an additive layer manufacturing technology. It precisely deposits production-grade thermoplastics in a layered method to produce a finished part. For the project that we're working on, we started with our CAD file and put it into the FDM software called Insight, which was able to slice our file for build, prepare the process or the CAD model for being consumed within the FDM Fortis system. Once the file was processed, we put it into the system for build, and out the result comes out a part complete, ready to go. In our particular case, our wing was built without any internal support geometry or material, and the part was able to be taken off the build sheet and go directly to the post-processing steps for marrying with the aerosol jet technology. So aerosol jet. Aerosol jet is Optimec's product. It's a print head by design that uses conductive or a variety of different kinds of inks that can be atomized and then collimated and then deposited on complex surfaces, as Jeff mentioned earlier, with a high velocity stream. You see in the video here how the head is moving around and you see the ink being deposited on that flat surface. The technology, aerosol jet, starts with a reservoir of ink. It then excites that ink into an atomized mist and then feeds it through the nozzle, which creates a highly collimated stream of ink so that it can precisely place that stream of ink down on a surface. The fact that it has a standoff distance, you can see here on the chart, apologize, I don't have my pointer on. Let me get my pointer on. So right here you see that the ink is coming out at it with a standoff away from the part. This actually played favorably in our project by allowing us to print over the curvature of the wing without having to go to 5-axis control. So here's an image of one of the parts that we were actually printing for our project. The inks that we had to select from are pretty vast. Optimec has a wide range of inks, from conductive to dielectric, adhesives that can be used for surface mounting, but a wide array of different materials can be used to print your part in different variety of sensors, and I'll talk to you here in a moment about all the different items we pursued. So what did we take on? We took on the FDM process to build the wing, and that wing had to be compatible with the aerosol jet process. So 2 criteria came out of that. One, we wanted the wing to be representative of the typical application of a UAV, so the mechanical strength and the high heat deflection temperatures had to match the application. Aerosol jet inks, nanoparticle, the aerosol jet material was the nanoparticle silver ink, Cabot CSD23. This material requires a heat centering to get the bulk material for the conductive properties of that material up to the highest level possible. And that centering process occurs at 300 degrees F. So you see now that folds back into the heat deflection requirement for ULTIM. ULTIM has a heat deflection temperature up around 330 degrees F. So now we knew that this part would withstand that centering process. So the 2 technologies have to map together to result in a final product. And I'll talk to you now about how that process occurs. So first you want to design your part, both the structural part, in this case the FDM part, as well as the electronics. Whatever you're going to build has to be designed prior for the 3D definition. Once you've got your design, you can build your FDM structure. Once that structure is complete, you go through and do surface prep on the FDM part. One of the lessons that we learned out of our trial was that the inks that Optimec can deposit did not perform well with our low surface energy ULTIM material. So as deposited, the materials would beat up or run into the cracks. So we had to come up with a solution to get those 2 to be compatible. What we found was that a simple sanding or soda blast of the surface of the part roughed the surface up enough to provide the required surface energy to allow ink deposition to go extremely well. We also found that building fixtures was very beneficial to the process to index those underneath the print head. And we did that because there's several iterations of printing. I talk here about the surface prep of on the ULTIM side, on the Optimec side. The surface prep here, we applied a self-leveling compound of a dielectric ink that smoothed the surface as well as filled in some of our build ridges. With this deposition, we had to locate the wing at a precise location under the print head and then print that 3D pattern down on the part. Secondarily, we came back and printed the conductive ink. So having that fixture be able to load and unload parts for each of those processes allowed us to accurately position that under their print head for each step. Once the conductive patterns were printed, we went to the oven for centering. As I talked about, we had to center the ink to 300 degrees F to get it to fuse together, essentially, and increase its conductivity so that the parts reached a higher level of conductivity. Then finally, we went back into the fixture and put it back into underneath the print head and put a dielectric coating over the top. This protects the part and keeps the sensor from being exposed to the external elements. So we went completely from design through finished part with the two technologies and understood a variety of issues that we had to solve to get them to be 100% compatible. So what kind of electronics can you print, and what kind of things are of interest in this domain? Well, there's three basic categories: sensors, circuits, and electronic components. In the sensor side, think of resistive temperature detectors, heating elements, antennas as we used in this project, strain gauges, and even chemical sensors. So the ability to put a robot into an environment and sense what kind of chemicals, hazardous chemicals, might be in the area. Those are all possible with these kind of technologies and printing these circuits. Then from a circuit side, the power, signal, ground planes, RF strips all have slightly different requirements. A power circuit requires the highest level of conductivity possible. If you run a lot of current down a highly resistive circuit, you'll get essentially a heating element, and it would heat up, potentially burn or destroy itself in the process. So you have to be able to create a signal circuit that can run whatever device you're trying to power. On the signal side, it's almost the opposite. You're trying to get as little material down as possible to minimize weight, and just enough to be conductive enough to operate the signal. So your light goes on, your light goes off, just as minimal as possible. Ground planes, RF strips, have similar kind of requirements. The electrical components are like resistors and capacitors. Because you can print conductive and dielectric in series and then in layers, you are at you have the opportunity to print these kind of components. One of the things that we took great advantage of on this project was the surface mount connections. I'll talk in a moment about how we surface mounted an LED, and then with their system we're able to print up on top of that from our surface of our part right up onto the LED to power it. So there were no connectors, no wires at all in our assembly. All right, so down to the details of exactly what we did on this UAV. We teamed with Optimac. We also pulled in Aurora Flight Sciences because we wanted to get real live requirements. We wanted to understand what kind of performance measures would be required to meet in order for it to be a success. So for sensors, we picked two things. We picked a slot antenna that would project video signals. We had a camera connected to a video head, and then that driven across the antenna through Wi-Fi to a receiver, and then projected back on a monitor. And that antenna was demonstrated as functional. On the strain gauge, it's very typical of a wing of a UAV that they want some sort of active feedback on wing loading. So a strain gauge at the root end of the wing is very common. So we wanted to test how well the FDM process could print these very, very fine features, and then how accurate that strain gauge performed. For circuits, we did a power circuit, which ran a real motor that was typically used with UAVs and carried almost a watt of power down it. On the signal side, we used the LED as an indication that we could turn on and off a flashing LED, and that was driving the signal down a circuit. So what happened? What were the results that we came out with? So on the signal circuit, we printed those at 100 microns wide by 20 microns thick, and printed the traces right up onto the LED. And you can see right there that the LED is glowing and actually flashes as long as you drive power to it. So that was extremely successful. We're very happy with that. The power circuit, we printed at 1,000 microns by 60 microns, 1,000 wide by 60 thick. And we powered a 20-volt half-amp motor, which is 1 watt of power across that power circuit without any resistive heating and any kind of negative performance. So this is the power circuit here in the image, and I apologize for not pointing this out before, but that's the LED. So both of those worked real well. We did learn a lesson. Well, first I'll cover that these were all printed in less than 30 minutes. So although it's not a production rate, high volume type of number, it is for custom, one-off, low volume. This is an amazing capability to be able to print custom circuits on a 3D part in minutes. One of the things we did learn on the project, FDM thermoplastics, Ultim in particular, has a CTE value of 4 times 10 to the minus fifth. That's a fairly high CTE value in relation to metals, which is 10 to the minus 6 number. So an order of magnitude different. So we do have a CTE mismatch between the metal conductor and the Ultim structure. So we use that dielectric material as a bridge between the two to minimize that the strains, that the localized strains that were being created for a high temperature delta, which was part of the sintering process. So under normal conditions, the CTE delta, the mismatch, is not terribly important. But under the Cure sinters process, you can literally crack your deposited circuits or sensors just in the sintering process alone. So that has to be identified and dealt with through your dielectric material, your printed material, and your FDM material. It's one of the lessons learned from our project. On the antenna side, as I mentioned before, the slot antenna produced video quality transmission over a Wi-Fi network. The interesting things that we learned out of this is that printing wide surface areas and then being able to manage a very narrow gap, those were critical elements of this antenna. So being able to manage those appropriately is very important. So we used a wide nozzle for the area and then a narrow nozzle to come in and print the very fine features. Got very, very good results. Now, what we didn't achieve was the strain gauge. These were being printed at 100 microns, very fine conductive traces, and you can see the magnified view here of each of these traces are the lines that were deposited. This is actually right here just a pad for terminations to the signal processor. So what we found is that these, because we didn't want to print on the dielectric, which might mask the strain in the wing, we were trying to print directly on the Ultim. And because we were attempting not to sand the surface completely smooth. We were trying to work with the as fabricated surface minus just the grip blasting. And we found that we couldn't get the traces to be consistently conductive without localized errors. So we'll have to find a different way to marry strain gauges to the surface, whether that's through a dielectric that doesn't mask the strain, but that's an ongoing effort that we need to work on. So in summary, what are the advantages of what we learned? Well, we've proven that we can marry the electromechanical design at a digital level. We've realized the flexibility that we obtain from design optimization and the ability to change that design as we learn more about what worked and what didn't. In addition, cost reductions from smaller bill of materials and fewer processes helped us to eliminate a lot of additional costs that could occur in these kind of products. Eliminating the tooling and the labor for assembly is another great advantage for both cost reduction, but also feeds into cycle time reductions. Your production development and manufacturing times are radically reduced with these kind of combined technologies. So just to give you a picture of the final product, this is a demonstrator that we created to take out to a variety of shows and just put in people's hands. The actual parts that we talked about before were actual functional large pieces, but we did reduce this down to a demonstrator. It's got a 13.5 wingspan, inch wingspan. If you see it at the shows, you'll know what you're seeing. It takes about 6 hours to build one of these in FDM and an hour to print it at the aerosol jet. It does have functioning motors, LEDs, and then the slot antenna and the integrated contacts are there so that you can see them, but we don't have anything hooked up to them to demonstrate those. So R&D for future activities. First, want to make sure everybody understands what considerations are important. Surface finish, the surface energy, knocking down or increasing the surface energy of the ultim parts to get the inks to deposit consistently. Make sure you consider CTE mismatch and how you're going to manage and handle that. If you're going to use a sintered ink, then you want to make sure your heat deflection temperatures and your materials match. In the future, we want to start looking at how are these technologies brought together. What are the design rules that we need to document and put together for users? What are the kind of interface requirements that we should be looking at and how to document those? And then performance expectations. What can you expect when you marry these two technologies? What are the performances you can expect for the variety of sensors and circuits and devices? And then finally, as we have learned already, with our demonstrator models going to shows and being shipped and traveled and handled, how fragile are those? How do we repair them? How can they be modified if we want to add additional circuits on it? These are all things that happen in a regular design product, so how can they be accomplished with these kind of new processes? So we look forward to documenting those and getting those out into everybody's hands. And without further complication or discussion, I will hand this back to Jeff to give you the future vision.
Well, the future is pretty exciting on where this technology goes as the technology readiness level continues to rise with all the details that Bill provided you on the material and process. And, you know, when you start thinking about all the technology integration, particularly for like robotic systems and sophisticated electromechanical systems, the potential of doing in-situ process control, having closed-loop feedback, is things too hot, things too cold, what are pressures? To be able to do that is pretty exciting for us, what the future holds. Then you say, okay, what applications does that go into? And we really think that because the additive manufacturing technology, particularly FDM, can actually mimic organic shapes very easily, that the ability to do various types of prosthetics that could maybe improve a person's life who's lost a limb from an accident or one of our veterans or something, of integrating, doing those organic shapes and integrating the the electronics into the circuitry to provide the motion control is pretty exciting, and it's not Star Trek-y. There's a number of activities going on in the States and worldwide on this front that now with these two key technologies, we could just accelerate those concepts to pilot, and then from pilot to production commercialization level to improve quality of life. So that's what we think is pretty exciting about what the future holds for us, and we think that we'll see incremental things come out in the next 2-3 years, and then 3 years and beyond. Boy, it's whatever you can dream, you could pretty much make.
Wow. Thank you so much, Jeff and Bill. This is amazing. In a minute, I want to let everyone know we'll take any questions that you may have, and if you think of a question in the meantime, be sure to enter it in the Q&A panel. And I wanted to let you know that after the event, you can download a copy of the slides and the recording of this webinar at stratasys.com/webinar_smartparts. And if you want more information and have an actual application for this, want to talk with the experts, there's some contact information on the screen as well for Optimec and also for Stratasys. Okay, now on to the Q&A portion of our event. It looks like a few of the questions have started coming through. We'll try to get through most of these before our time runs out. There's one here from Todd. He is asking, and actually I'm going to direct the questions to Jeff first, and Jeff, if you want to throw them at Bill, go ahead.
Sure.
As we go here. So Todd is asking, does this work with all material combinations, as in all FDM materials and all aerosol jet materials?
So our work to date has been primarily with the all-temp materials that runs on the Stratasys FDM machine. We have 10 other FDM materials from ABSs, polycarbonates, and versions of those materials that we feel very confidently the aerosol jet technologies would work fine with. So that's the answer there. Now, beyond FDM materials, Bill talked about surface preparation, surface energy. There are a number of other materials and substrates out there from other types of processes that this would also work very well with. But we're confident that aerosol jet works with a number of different materials, and it works well with the FDM.
Okay, thank you. Here's another one. Shane is wondering if the two technologies are integrated, are you able to embed electronics built within the FDM walls?
I'm going to defer this one to Bill, since he's a little closer to the technology than I am, and get his perspective on that future state.
Thanks, Jeff. If the parts were, if the two technologies were actually integrated, which to date in the current state they're sequential, not integrated. We do suspect that this will be a good integration to be able to print like the LED we printed up over the surface of that LED to make the connections. That would be a very similar application. How we would trace up over layers our Z-axis layers in these builds. So we do see that not only embedded but as well transitioning the Z height are possible in the future if and when these two technologies are integrated.
Great. Thanks, Bill. Here's another question. This one's from Janice. She wants to know how big you can go with each technology.
Well, with the FDM, our largest machine out there is what we call our Fortis 900 MC, which does basically a 3-foot by 3-foot part as far as individual build. Now, you can piece these together, take a 3-foot section, add to another 3-foot section to do a 6-foot section, and et cetera, to make bigger parts. But and then the actual build volume or build size on the aerosol jet is a 470 millimeter by 370 millimeter XY build. But you basically could have the ability to take a 6-foot part from an FDM machine that's been assembled and be able to kind of have an infinite build from side to side and feed it through the aerosol jet system to do various sizes from small. The examples Bill gave were wings approximately 14 inches in overall length to parts that could be potentially 14 feet in length and just fed from the left side and coming out on the right side.
Great. I think we have time for about one more question. Here's one from William. He mentioned he may have an application for this, so he wants to know how to proceed. And I think I'll direct this one to Bill.
So if somebody has a project that they're interested in getting going, either go through the address or the contact information that Kim provided earlier, or give us a call at Stratasys or Optimec, and we'll kind of understand what your requirements are, understand where you're going, help you down through the design process, and then see if we have a closed solution that will help you solve your problem.
Great. I hope that helps William with his question. Well, it looks like our time is about up. If we didn't get to your question live on the call, we'll be sure to follow up with you afterwards via email. Thanks again to Jeff and Bill, our wonderful presenters, and thank you all for your attention during the presentation. Now I will turn it over to our operator, who will close out the event. Have a great day.